Sure.
Okay, so yeah, we are very happy to have Matthew Hernandez from University of Maine to come and give a talk at our early career math colloquium. And Matt got his PhD from Princeton in 2017 under the supervision of Charlie Pfefferman. And his main areas of research is in the PDEs and fluid equations. And yeah, like I said, we're very happy that you are here, and go ahead.
Okay, thank you very much to the organizers. I'm glad to give this talk. So today I'm going to talk about splash singularities for the MHD equations, and specifically the ideal MHD equations. And we're going to be interested in a particular special case of this, and I'll elaborate more on that later. So first of all, I should explain what a splash singularity is. Oh, of course, this is joint work with Diego Cordova and Alberto and Pisco. Right. So what is a splash singularity? So first of all, we should be thinking of a fluid equation with a free boundary. And I want to talk about a specific example. So just to keep things very simple, let's talk about the water wave equations. So the water wave equations are basically just given by taking some smooth interface. So you can think about this as the height of the water or something like that. And let's say this curve is parametrized by x of alpha. And please tell me if you can't read anything. I'm happy to clarify whatever you can't read. But anyways, we have this curve which delineates the boundary between the vacuum. Let's say it's total vacuum, there's no air, and the water itself. And in the water, the velocity satisfies the Euler equation, which are dtu plus u dot grad u. This is kind of the acceleration, and it's balanced by the forces. So we have the gradient of the pressure, and if we want to talk about gravitational water waves, we usually add some force due to gravity. Now, of course, we need this to be divergence-free. You can always study compressible Euler equations, but in particular, incompressible Euler equations are particularly interesting. And let's see, we also need some boundary conditions. So the pressure, let's say this region is omega, then the pressure is 0 in the boundary, okay, or some constant.
I have a question.
So this is the one. Oh, yeah.
Yeah. So you use Euler equations. So why don't you just use Navier-Stokes equations?
So that's another very interesting case. You can do Navier-Stokes. It is much more difficult, but it is done. And I'll explain. Actually, we'll see why it's so interesting to do one case versus the other very soon. Okay.
Okay. Sure. Thank you.
Question. Okay. So let's keep it simple. Think about the case where there's no viscosity. Otherwise, there would be a Laplacian floating around in here. And think about adding friction to the problem. In some cases, it makes things more nice. In other cases, it makes things more difficult. So we have this, and even this will be difficult in this simple case. What we want to ask is, how do you start with a shape like this? And then let's say that the curve evolves into a shape like this, where you can imagine two waves emerging and colliding with each other in finite time, okay? So even this, in this relatively simple looking case, is quite difficult. And the first time it was proven that this was possible is pretty recent. I'll get more into the specifics of that in a minute, but let me explain at least roughly why it's hard, at least very vague sense of why it's hard. So why is this difficult? So in general, water waves is a very challenging problem. But in particular, I would say, now that it's well known, local well postedness is, like, we could say standard in some special cases. And one of the very well-known conditions is that you would like for the chord arc condition to be satisfied. Okay, so the chord arc condition is basically the condition that you are not in this scenario. So the way to formulate it precisely is that the supremum of some quantity I'm going to write. So I'm going to have two numbers here, alpha and beta. And x is the parameterization of the curve. So if we take x of alpha minus beta, this difference quotient, divided by alpha minus beta, and then we invert this thing, the chord arc condition is the condition that this is bounded. So what you can imagine, maybe for simplicity, is that you have two maybe starting points, alpha and beta. I'm cheating a little bit because these are numbers, not points in space, but it's pretty much the same. So you have these 2 points here, and then eventually they get mapped to the same point. Let's say alpha prime equals beta prime. If we follow their trajectories, we follow where they go. And in that moment, we have 0 here, but something non-zero here, right? If x is, well, I should really say this is x at time 0. This is x at time t, right? Where t is the time of splash. But the point is that at that time, this ratio, if we invert it, becomes infinite. So in this case, the supremum of that stuff is infinity. But in this case, the supremum of that stuff is finite. Okay, so we're not in a position where we can easily prove well-posedness in a neighborhood of this data. Okay, is that okay? Okay.
Yeah.
And there's some interesting reasons for that. Oh yeah.
Yeah, I have a question. So for the, I understand one alpha equals beta equals 0, then you have the supremum that equals to infinity. But
Yes.
what does it mean physically? Does it?
Yes, that's a good question. So, I mean, physically, it just means that the parameterization of the curve has a shape like this, or if it doesn't, if the supremum is not bounded, you know, it's somewhere in a neighborhood of this. But in terms of the solution to the problem, it has an important role.
Okay.
So essentially, let me take a simplification to the system. Let's assume that the fluid is not only divergence free, but also curl free inside, okay? This is a very common simplification. If you do not make it, the equations become much, much more complicated, but you can do this. If you do this, the equations become reformulated in terms of a one-dimensional problem. There's some function, let's say phi, and it kind of lives on the boundary. And what you can really think of is like, a lot of people like to say is that the curl of u is 0, right? But in fact, you can think of it as though the curl of u is a measure, and the measure is supported on this curve, okay? And whenever you can recover a velocity field from the curl by using a Biot-Savart law. So I'm going to be very sloppy here. Hopefully it's okay. So I can't remember if this is going to be n dot x or n of x or n of y, but you have some sort of kernel here, and phi of y is here, and you have some sort of d sigma. And the idea is that you're integrating actually over the curve. Again, I'm being very sloppy, but in the case that the curve is like this, what you will find is that the kernel will have a cancellation when you integrate, because you're integrating over the curve, and when you go around once, you're coming from this side, and the normal is pointing one direction, and when you come around from the other, the normal is pointing the other way. So what you find is that there's a degeneracy in your operator, which means that it becomes difficult to invert this. It could be that the output must be small, even if the input is very large, for example, because of this cancellation. And so, but in reality, this is actually a technical difficulty. But if you're writing things in terms of phi, you have to learn how to deal with it.
Sure.
Yeah. Yeah. Very good question. Okay. So how do we get around this? So the first proof It's a large group of authors. So try to get the names. First, construction of a splash for water waves. List of authors. We have Castro, Cordova. They're all joint work on this paper. Pfefferman, Canfero, and Gomez Serrano. So a lot of authors in this paper. And so their idea was that we take this, this water wave system, and of course we look at the case where we have these conditions that simplify things. And a really important thing is that if you think about it, this means there's a very special structure in the equations. It means that you basically solve a Cauchy-Riemann type equation. So if I should get the numbers right, because it's flipped from the sign and the typical Cauchy-Riemann equations. But what it means is this. Okay? So this is essentially the Cauchy-Riemann equations. Of course, there would be a minus here and a plus here, but it's the same. So we have this structure. So what's really helpful is if we can make a conformal change of variables. Conformal change of variables, which is going to make life a lot easier. And it seems almost obvious when you see it, but the reason we want it to be conformal is that it's going to preserve the structure, this very nice structure which we like to keep. And what we want to do is actually take as the initial datum the water in the splashed configuration. And ultimately what we would like to show is that we can make the waves come apart. So if we can go in this direction, it would be nice. But why does that mean the opposite thing can happen? How does it mean we can start here and arrive here? If we can show this, well, it would be by reversing time. Of course, we cannot reverse time in the Navier-Stokes equations because of the viscous term. That is a different problem, and it is much more difficult. I don't have time to talk too much about the techniques they use there. Let's assume time is reversible. Well, let's assume we have no viscosity, Euler equations, it's time reversible. So what we'd like to do is show that you can start here and end here. Reverse time means that you can start here and end here. So what do I mean by this conformal change of variables? What I'm actually going to do is take the square root transformation with this branch cut. So z maps to the square root of v. And that's going to transform this problem. Again, it seems almost obvious in retrospect, into a new problem and a new set of coordinates. But the picture will look something like this, right? We'll have an augmented set of equations here. And all that we have to show is that as time goes forward, these two humps move below the branch cut. That's equivalent to that. So you take this system and you prescribe some initial velocity, which is going down. You do that same formulation I was telling you about how you have the curl is a measure on this curve though, and then you don't have this degeneracy of the operator in that world, right? Okay, so you have the augmented, I'll just say AUG for augmented water wave here, and then you can use this to get it WW could be water wave, a genuine solution to your water wave equation here, in which you observe this happening. Okay. Okay. Okay, so a natural follow-up question, and again, I'm doing a lot of setup before I'm going to MHD, but hopefully it's justified. So a natural follow-up question to water wave, which was actually the motivation for working on this problem. So follow up to, let's say, a water splash would be a problem that I would call a drop singularity. Okay, drop singularity. So now what you can imagine is that you have some fluid and it starts as a nice smooth interface. And then instead of it forming two peaks which crash into each other above, it's squeezed from the inside. So you have fluid here and here, obviously. So it's the inverted picture and flipped upside down, but it's much harder. No one has been able to prove that this can happen. You have this pinch here for the water wave equations. For some reason, it appears that when you try to push the water, it pushes back in some sense. And so far, there have only been negative results, so only shown impossible in some special cases. In particular, let's say for water wave, I'll put 4WW. Let's say this is parameterized by x of alpha. So in cases where x of alpha has some smoothness. But this is not very satisfying because we see this happen in day-to-day life. If you turn on your faucet and you look upside down, a water droplet will form. So it's very perplexing why we can only show so far that it cannot happen. Now, what you could suppose is that maybe with some roughness near the pinch, it's possible. And so you have this game of how bad must it behave in order for it to be possible? Can we prove that this happens? And so far, no one has been able to show that it happens. So I think that first step in this direction is to think about special kind of MHD splash. And it's not quite this, but it has a similar picture and it's easier. So I'll just give you a quick sketch before actually showing you the equations for MHD. But let's suppose that you have a free boundary problem. Now MHD means that there's a plasma. So this is a plasma. And then here we have a vacuum. But in the vacuum, we have a magnetic field. And I want to focus on the special case where the magnetic field is nowhere zero, or at least non-zero somewhere. And let's ask if a splash can happen. Okay, so what we find, again, this is the plasma, and the magnetic field also lives here and here. The magnetic field is forced and it's squeezed in some sense as this happens. The magnetic field actually has to be tangent to the boundary, so you can imagine the field lines actually getting squeezed here. So the question becomes, is this possible? Now, it has been shown that MHD splashes are possible, but only when the field is zero. So it's known MHD splash possible. I'll just say pause period. And results were on this recently this year. So there was a 2D result. Let's see if I can make sure that the authors. 2D result due to Howe and Young. And they actually do it for Navier-Stokes, so with viscosity. And there was a 3D result due to, let's see, Hong, Luo, and Zhao. Okay. And I believe they both do the viscous case, which is quite different. It's very difficult, but it is where the exterior field is zero everywhere. Okay, which is not always the case in the real world or in a tokamak. And in particular, if we want to think about the droplet problem, we're particularly interested in the case where the thing getting squeezed is non-trivial. So that's what I'd like to consider. Okay, so now what I'd like to do is, in particular, because the result is known for the case where the magnetic field is zero, is talk about the structure that H must have when such a thing occurs. So that's what we're going to focus on for now. So let's think about what, well, first I should tell you what the MHD equations are. So let's look at MHD. And then we'll think about the structure that the exterior field must have in order for this to occur. So in this little box, I'm going to draw a little blob of plasma. Okay, so here's my plasma, and I'll call this domain omega. And in this blob of plasma, we have a system of equations. The velocity field is going to satisfy ut plus u dot grad u. Now that the acceleration is balanced not just by the gradient of the pressure, but we also have a term incorporating a magnetic field inside. We have b dot grad b, and then we subtract off the pressure gradient. Now, because of the forces in the system, we no longer have to incorporate gravity and to have stability. So we actually don't need gravity in this problem. Of course, you could add it. And okay, the divergence of u is 0 inside. Okay. And now I have an interior magnetic field, INT, magnetic field, which satisfies BT plus u dot grad B equals B dot grad U. And the divergence of the B field is also 0. Okay. Now, as I said, I also have an exterior magnetic field, which is very important. I'll just say outer magnetic field. In reality, there's just one magnetic field, which has a jump discontinuity as you travel up and down. But because the equations that they satisfy are so different, I'm going to give it a different letter. So I'm just going to say this magnetic field is given by H. And in the exterior, H satisfies these equations that we saw before. Namely, its curl is 0 and it is divergence free. So whenever I write grad perp, if it's not clear, I just mean you take negative D2, comma D1. So you just imagine taking the vector and rotating it 90 degrees counterclockwise. Okay. So I have these systems, and now I have to add my boundary conditions. So on the boundary, I have B dot n must be 0. H dot n must be 0. And the pressure is equal to 1/2 the magnitude of the exterior field H squared. Okay. So it's no longer 0 as it was in the water wave equation. Okay. So that's the system. So let's think now, what does the exterior field have to look like if the splash is starting to occur? Exterior field structure. Okay. So let's imagine a splash is starting to occur. Okay, and let's think about what the field lines have to do. So remember, H is tangent, right? So its field lines are going to look something like this. So these are potential field lines of H. So what you'd observe is that because it has to be tangent, it looks like they're very tightly packed in here, right? So question is, do tight field lines create strong forces? In particular, forces which would prevent the splash from occurring. That's the question, right? That's what is counter to your intuition. Or I should say, your intuition says that when you try to push two magnets together, you see the field line doing something similar, and obviously they don't want to touch, right? So you might suppose they're fighting. But I would claim that it depends. The answer is maybe not. So it depends on the scenario. Okay. Now, the reason for that, if you think about this a little more carefully, it becomes pretty clear. So if you have a completely closed shape like this, I'm going to draw what these field lines could look like when possible configurations. Inside of that, we have grad perp dot H equals 0, del dot H equals 0, and H dot n equals 0, all inside here, right? And H is smooth inside here. So you can actually use a divergence theorem to prove that H is 0 inside the cavity. Now, another way to see that is that you could write H as the gradient perpendicular of a stream function, and you would almost immediately find that that stream function has to be constant everywhere inside. So if this is a scenario, it looks like H must be trivial for a splash to occur. Somehow it becomes weaker. And the idea is that in this picture, every field line which enters must also exit, and the net flux will actually be canceled. But that's not the whole story, okay? So when you look at this picture, you then wonder, maybe a different type of splash, must H go to zero as the splash happens, okay? And I claim that the answer is maybe not. And eventually the answer is no. So I'll explain the construction of it later. So maybe not. So this was a very special thing that we considered. And the key thing that we assumed was that H was smooth on the inside, right? Now, in reality, if I have a plasma, maybe it's in a tokamak, right? And what I can do is say that it's living in some bounded region, right? These are like the walls of my chamber, my plasma chamber. And I can also stick a little wall here. And you can imagine, maybe this is the core of my tokamak or something, even though it's two-dimensional. And the plasma is wrapping around. And what this means is that I could take this picture and instead I could consider H's that have a singularity here, and then I could hide the singularity kind of beyond the wall. Now, technically, if I define my vacuum to be the area, the shaded region, H is smooth in the vacuum, right? But perhaps by adding singularities, I can create H's for which this argument does not hold, and for which it may be non-trivial. That's the idea, okay? Another thing is that in 3 dimensions, this argument does not work. So it's also an interesting question to think about the 3D case. Okay. So now let me think about this a bit.
So does that kind of scenario exist for compressible MHD or compressible Euler?
This is all incompressible MHD, but I think compressible is probably a similar question. I think you could ask the same exact questions for compressible. It would probably be more difficult though. Yeah.
Thank you.
I think that one of the issues with compressible is that you have to watch out for the formation of singularities. Because compressible equations lend themselves to shocks and things like this. But it'd be very interesting to think about compressible equations as well, certainly. Yes. Okay, so now let's think about, check time, okay. Let's think about some potential structures for H in these splash regions. And in fact, now I'll sort of lay out what the game is. Okay, so the game is to construct a good H. So find some sort of H. So think about, let's think about separating the dynamic problem and the H problem. So let's produce or try to produce an H, which is non-trivial. But maybe I'll just write as this, even though that's sort of a little bit ambiguous. It's non-zero, at least at some point, for any near splash or splash region that you could draw. Okay, and then what we'd like to do is import this H into the dynamical problem. So the dynamical problem is going to create a region which involves a certain shape. And what we'd like to do is have a particular H in mind for whatever the evolution will cause to occur. So we need to have some flexibility. But we don't need too much flexibility. So I want to focus more on producing the H because it's already, this part is still in progress, getting the dynamical picture to be completely done, but it's forthcoming. But let's focus on producing an H, also given time. How do we produce an H for any near splash domain, which is non-trivial and which is well behaved? Okay, so the question is, what is the structure? For a good H. I'll put good in quotes. Okay, so what I want to do is kind of simplify the problem. We've been looking at this type of region, and we sort of consoled ourselves with the fact that we can add a singularity maybe to make things interesting, right? So H lives here, and we've decided that it's okay to prescribe that perhaps H of 0 is infinite if this is the origin, okay? So we've been looking at this picture, and what I want to focus on is, let's say vaguely what kind of thing does this look like? So I'm going to replace this by a simpler picture. So let's just say this is a simplified picture. If we have two balls, I should draw them closer together, of plasma, moving toward each other, maybe this one's omega 1, this one's omega 2. And let's say that their separation is distance delta, okay? And now we're going to create an H in this picture. And what we want to think about is, instead of having the singularity at a finite point, we might as well take the singularity at infinity. Right? There has to be a singularity somewhere to get something non-trivial as this closes, or else we'd be violating Liouville theorem. But right, so let's take that singularity to be at infinity. Okay. So an equivalent problem to finding the H that I described is to find a stream function for H. Okay, so the stream function, we'll call it phi, has to satisfy, and we'll call this V is the space outside of these two balls, right? So V is for vacuum. So we need Laplace phi equals 0 in V, and we need that phi restricted to the boundary of, let's say, omega I, like omega 1 is the right one, omega 2 is the left one. It has to be constant on each of these. Now, the reason it has to be constant is that we know that n dot h equals 0. And what we're going to do is take h equal to the gradient perpendicular of phi, not the gradient of phi. So when I take n dot h, I'm taking n dot grad perp. That's the same thing as rotating the n vector, and I get the tangent derivative of phi. So if phi is constant on the boundary, the tangential derivative will be 0. So h dot n will be 0. Okay. So I want to find a phi with these properties. And I want things to work out nicely. So let's take a first try of finding such an H. Very explicit try. Because now things are looking sort of simpler, right? So I'm going to say here's a perfect circle. Let's just take perfect circles for simplicity. And let's say phi equals -1 here. And let's say phi equals +1 here. Right? So this is like a very simple problem that I could solve. And especially if it's two circles with separation delta, you can actually calculate explicitly the most obvious solution to this. And it's going to be phi of z is equal to some constant c. Let me erase this. I would divide by some delta tilde. So delta tilde is not exactly delta. It's more like the square root of delta, but they go to 0 together. And then here I would have log of z plus delta tilde over z minus delta tilde. Now what's happening here is you just take a Mobius transform that basically maps the vacuum here to an annulus. And then log is going to have a certain value on the outer ring and the inner ring. And you will find that phi has this form. So this is a very nice try, but what you'll actually find is that something goes a little bit wrong. So the problem, okay, let's think about what happens as delta shrinks. And I look at this quantity. As delta shrinks, Okay, this is log, right? So this is log of z plus delta minus z minus delta and dividing by 1 over delta. So that's like a difference quotient. So what we find is that as delta goes to 0, this phi, I mean, it depends on delta, but I'm suppressing that. It starts to look like the derivative of log. And so that means it's going to look like the real part of 1 over z. Okay, that's the idea. Now that might be okay. That might be okay. Except if you think about it, that means that h, which is like the derivative of phi, is like 1 over z squared. And if we have a magnetic field, we want its energy to be finite. Now what you'll find is that in the limit, as delta goes to 0, I'm cutting away much of the singularity because I'm only going to integrate, the energy of h over the vacuum. But even despite that, what you'll find is that this energy, so you just take the energy of this, we're actually going to remember because the vacuum, it lives inside a finite chamber, so we don't go all the way to infinity, but we cut the vacuum around this, and yet we still get that this quantity will become infinite as it closes, because this is just too singular, okay? So while this is an easy and explicit first try, it's not quite right. However, it is like a very important function to the problem, okay? And in fact, this is equivalent to the case where I am 0 here, and I am 1 here, and then this is the harmonic measure for the region, essentially. It's a very important quantity. It's the harmonic measure. So we'll talk about the harmonic measure and the role that it plays in a minute. So it's an important function for the system, but it's not the stream function that we want. Okay. Check time. Okay. So, and let's be a little bit more ambitious. Let's see if we can do things. Okay, so that was a bad first try, but let's try if we can do it again. And for maybe not perfect circles. So I'm going to imagine 2 blobs. Okay, be a little more general. And what we want for a good phi, good phase function, in particular, is that we don't want that as delta goes to 0, we get that the H field is 0 everywhere. And B, we don't want that as delta goes to 0, some sort of energy becomes infinite or some sort of force becomes infinite. That's exactly what we want to avoid to make this possible. Okay, so remember before we did say that phi had to be C1 and C2, but now what we figured out is that in the limit, we must have that C1 equals C2. So we're going to try to find phi which is 0 here, phi which is 0 here, and yet somehow we want phi to be not 0 everywhere. That's why it has a singularity of infinity, for example. Okay, so let me explain a little bit more the strategy. So the first step is going to be, we're going to use the harmonic measure, which is that quantity, it's the general analog to that function I was writing before. For, let's say this is the vacuum region V. So we'll call this mu vacuum of x, y, or z. This is just the harmonic function in the exterior, which equals 0 here and 1 here. To conformally map this to a canonical domain. Okay. And then we're going to see if we can find the suitable phi tilde, and I'll call this domain v tilde in v tilde, and then 3 is going to be that we're going to take. Okay, wait, so mu z is the conformal map, but I'm going to call that conformal map f delta of z. And then what we're going to take is phi equals phi tilde composed with f delta. Okay. So we have to think about what is the most fundamental conformally equivalent region to the vacuum here. And the answer, if you imagine the Riemann sphere You're taking the Riemann sphere and you're cutting away, let's say, a little blob here, a little blob there, and you get a band which goes all the way around the Riemann sphere. So if you push that band down, you get an annulus. So we have an annulus, and I could unravel that annulus, and I get a long strip. If this distance is delta, then what we'd find is that the dimensions of this are asymptotically, should be explicit. Let's just say 1 over epsilon. But yes, epsilon is like the square root of delta. This is very roughly speaking. So the tighter this is, the longer this is, if I fix the width at, let's say, something O of 1. And I'm going to think about where these different points go. So remember, phi is going to have to be singular somewhere, otherwise it would be 0. So what I'm going to do is decide that my phi tilde, which lives in this world, this is going to be v tilde, by the way. We identify the top and the bottom, right? Phi tilde has to be 0 on the boundary. Like this boundary could be this one, maybe this boundary could be this one. But it has to be singular somewhere. So let's take phi tilde of 0 to be unbounded, whereas phi of infinity was unbounded here. Okay, so that's what we're looking for. And we have this map F delta, which takes us here. Now, if you want to know what the harmonic measure has to do with this, the harmonic measure actually appears as the real part of F delta. Maybe I'll call this nu for the other piece. This would be the harmonic conjugate of mu v, because the harmonic measure takes the value 0 on this set and 1 on this set. So it's going to map this to this vertical line. It's going to map this to this vertical line if it's the real part, right? Okay. And then the nu is going to tell me how I wind up and down as I go around here. Okay. So I have my F delta, and now I have to find phi, which works for this region. Now, it turns out that there's only very particular types of functions like this, phi tilde, and a little tight on time. What we can actually do is take the Green's function for this domain, which is explicit. So, long story short, we can take phi tilde of z to be, so the Green function takes 2 inputs. There's a z1 which goes here, and a z2 which goes here. And the Green function has precisely the property that whatever you put here, if you run up and down the boundary of the domain, it will be 0. And that's what we want for phi tilde. The 0 here represents the placement of the singularity. The Green function says that we should take a logarithmic singularity and place it wherever this point is. So normally it would be at z minus z2. So it looks like log z minus z2. We're taking this special case. So it's very well known, and it's very explicit for the strip, and it has very explicit asymptotics. Let's see. So let's see. I'm running a little bit low on time, but at least I'll write down what I'll call this capital G. Or no, let's just write phi of z. It's basically like log of cos y plus cos x over cos y minus cos x. Okay, so cos is like exponential e to the y plus e to the negative y. And remember, as this pinches, this becomes very, very long and skinny. So if I look in this, as I go to the top and the bottom, I'm plugging in y, which is kind of at the top of the strip or the bottom of the strip. As a result, this is going to be something like, very roughly, log of 1 plus e to the negative absolute value of y. I'm neglecting some constants and things, but the point is that this function is particularly well behaved as I go to the top and the bottom. Okay, and the other piece of information here is that the top and the bottom correspond precisely to the space in between the two approaching parts of the boundary. So what we learned is that it's going to be getting vanishingly tiny, even though it's going to be non-zero in the interior. So it will not present an obstruction as the splash closes. It will not generate large forces, but it will be able to be non-zero. Okay, so that's the idea. And it has extremely explicitly computable asymptotics, and so does the harmonic measure. And in the end, basically what we learn is that the function that we're looking for, let's see, this is the green function. Right, so we have to compose it with this. And what you should imagine is that the original phi, I'm sort of jumping to the answer because I'm running out of time, is going to be like the harmonic measure composed with f, let's see, mu. What have I written here? This doesn't look quite right. Oh. Okay, well, I'm skipping ahead a little bit, but we have this, I've written this wrong. We know that phi delta composed with, phi tilde composed with f delta. I'll just write that out. Now, there's also some work, I guess I am running a little bit low. There's also some work that we have. I know I haven't stated a theorem yet. I don't have time to write it, but a main theorem would be that an H exists for a fairly generic set of splash domains. You can do it for this shape. You can do it for this shape, where you add singularities here. You would do it for other types of splash singularities. And you can compute explicitly the asymptotics where the splash closes. And it behaves something like, if we think about the distance up and down, like if I'm moving away from this, let's say that this point, if I center my coordinates here, let's say this is the point x, y, the asymptotics are something like, for the exterior field, h of y, they're like 1 over the, let's see, y, here we have y squared plus delta to the power of 3/2, e to the minus 1 over the square root of y squared plus delta. So what you want to think about is this creating some strong force? And the answer is no. This part is becoming singular as I move in here and here, and as delta shrinks to 0. But the fact that I have this e to the minus 1 over this, it will kill that, even though this is a negative power here overall. So we have explicitly computable asymptotics, and h of y is very well behaved in the limit. And forthcoming theorem will be when we are able to import these H fields that we create into the dynamical problem, which unfortunately I didn't have any time to discuss. And more forthcoming work is on other possible H's that you can take, because it seems that you can classify almost all possible H's which satisfy the requirements. Quick word about that, which I think is interesting. The main thing that we needed was to map this region to a strip, and then we're able to put a singularity here. And the simplest case was a log singularity, but more generally, I could take any meromorphic function in this strip. Okay, so I can imagine taking sum of finitely many singularities here. Okay. Now remember that it's 0 here and here. I can reflect it across the boundary by Schwartz reflection, and I actually am creating meromorphic functions in a lattice. And so those are the Weierstrass elliptic functions. So basically, given any Weierstrass elliptic function, you can create a non-trivial exterior splash field. And they kind of characterize, in some sense, all the ones that you would want or need for the problem. So that's, I guess I have 10 minutes left. So there's a lot more that I wanted to talk about, but maybe it's a good time to go to questions, since it's like 10 minutes to 4 here.
Yeah, okay. Yeah, so let's first thank the speaker, and then questions. I think Matt, there is a question in the chat.
Oh, okay. Is there an archive paper where the theorem is stated? Not yet, but hopefully very soon. Hopefully very soon.
Mhm.
Yes, in the next month or so, at the latest, I would say.
Any other questions? I have a question. So, maybe I missed the part of the talk. So, are there any classification for the singularities? How many singularities? Usual types of singularities.
So do you mean like in the fluid problems, free interface problems, or
Yeah.
specifically like oh, okay. Wow, that's a good question. I think let's see, let me erase this. I don't know if there's been any that have really been studied in depth besides the splash singularity.
Mhm.
But I mean, you can always break it down into two types, where one is a case in which there's a singularity happening on the boundary, and one is a case where there's a singularity happening inside the fluid. So I don't know of any case where people have constructed, let's say for water wave, to keep it simpler, a case where you have some sort of singularity forming around a point in the interior. I think the only cases that I know of, I could be wrong, about singularities for water wave are